All right, folks, so what we're going to be talking about are gas laws. And in particular, we're building off the knowledge from states of matter. So in particular, we're just going to be focusing our attention on gases and gases alone. All right, so first thing we need to have is a general knowledge of pressure, temperature, and volume. And so pressure, the key thing here with pressure is that it's a force exerted by a gas on a surface area. So it's force over area, okay? So if you want to think of it as like a formula, you can think of it as pressure is equal to force divided by area, okay? And we can measure that in a bunch of different things, such as millimeters of mercury, which is what we have there with the mmHg. We can have ATM, which stands for atmosphere, and we have kPa, which stands for kilopascals. And right here, what you will notice is I have the values set for what it is that they are equal to each other, okay? The one way in which we can measure pressure is by using what is called a barometer, and that measures what we call atmospheric pressure. And just so you know, we live under 1 atmosphere, in case you hadn't figured that one out. Okay. The other thing we need to know about is temperature. What is it? Well, it's the average amount of kinetic energy within an object. And we measure that using a thermometer. And in particular, for gases, we always want to measure our temperature in the unit of Kelvin. And the reason we want to do that is because Kelvin is an absolute temperature scale, meaning there are no negative numbers. The coldest temperature for Kelvin is 0 Kelvin. Everything else is positive. Okay, so there are no negative numbers with them. And that's going to be play a key role when we start talking about how we can predict what would happen to a gas if we were to change the pressure, the temperature, or the volume. All right. For the next thing, the last one is volume. Volume is just literally the amount of space an object takes up. We can either calculate it or we can measure it, and we usually measure that in milliliters or even liters. Okay, so let's talk about the relationship between pressure, temperature, and volume because they are interrelated with each other. The first one we're going to talk about is volume and temperature. Okay, and I need to go back here just for a second. All right. I do want to tell you that in order to solve for Kelvin, you take degrees Celsius and you add 273 to it. And the reason we do 273 is it's not just a random number that came about. It was actually done by looking at the volume and temperature relationship. So let's imagine this. Here's our question. All right. If you increase the temperature, what will happen to the volume of the gas? So if we increase temperature, the molecules move faster, and more than likely, because they're moving faster, they're going to cause it to expand. You've heard that. For example, hot air rises, and that means it is expanding. It is getting further away. So if you look right here at our graph on the left-hand side, you will notice that all of the gases that are being cooled down and looking at their volume and temperature, you will notice that they end up at this value of 273 degrees Celsius. That's where the idea of Kelvin came from. This is the lowest possible temperature. You'll notice that some of these lines are dotted, and the reason they're dotted is because of the fact that, ladies and gentlemen, they do not end up, we cannot measure their volumes. They literally become solids, okay? So if that makes any sense, so they're no longer gases anymore. They become liquids and solids, okay? Now, so what type of relationship exists here? If we look at the graph here, we have volume over here on the left-hand side. We have temperature down here on the x-axis. So we can see that we have what is considered to be a direct relationship, meaning if the temperature goes up, the volume goes up. If the temperature goes down, the volume goes down, all right? So there's a direct relationship between the two. When we talk about pressure and volume, all right? So let's ask, if you reduce the volume of a balloon by squeezing it, what happens to the volume? Or I should say, the pressure is what I should be saying here, all right? So if the volume is, if we take the balloon and we squeeze it, the volume's getting smaller and smaller and smaller. And if we're getting smaller and smaller, we're getting the particles closer and closer together. And as you can see here in my diagram, on the left-hand side, we've got a pressure of 1 atmosphere and a volume of 1 liter. And then what we do is we decrease the volume by half. When we do that, the pressure goes up by a factor of 2. It doubles. And same, if we take again and reduce the volume by half again, we then again double the pressure. So it would appear, ladies and gentlemen, that we do have a relationship between pressure and volume, and that would be inverse. As one value goes up, the other value is going down. Meaning, if the pressure right here, ladies and gentlemen, is starting up here, and we were to reduce the pressure, that means that the volume would start to, for example, increase. Okay, so if volume is increasing, all right, that means that the pressure will be decreasing, okay? Meaning if the size of the container is getting bigger, it has more area to hit, so the pressure is going to get less and less and less, and vice versa, okay? The other relationship is pressure and temperature, all right? And if, for example, we were to increase the temperature of gas, what's going to happen to the pressure? Well, if the particles are going to move faster and faster and faster, they're going to have more force. And when they collide with more force, that means they're going to have more pressure, especially if, ladies and gentlemen, the volume is held constant, okay? And so you notice how pressure and temperature and volume can all be related to each other. So in this particular instance, pressure and temperature are a direct relationship, meaning if we increase the temperature, the pressure will increase, and vice versa. If we decrease the temperature, the pressure will decrease. Give you an example. Has anyone here ever used, for example, those air cans that you can clean like computer components with? Well, as you continue to use it, what ends up happening as the gas comes out, the pressure is reducing and the temperature of the can gets very, 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 very cold, okay? And so that, ladies and gentlemen, is a great example of pressure and temperature. Let's take a look at the combined gas law. In particular, what we're looking at is the idea of how pressure, temperature, and volume are related to each other. Okay, and so here, ladies and gentlemen, here is the relationship between pressure, volume, and temperature. And you're going to say, well, what are the ones and the twos? Well, the one would be the initial pressure, initial volume, initial temperature, and P2, V2, T2 would be the final, okay? So if you want to really think about it, the one, ladies and gentlemen, would be the initial, and the twos would represent the finals, okay? So the final pressure, temperature, and volume, and so on and so forth. Now, here is why it's so important to use Kelvin, okay, for the temperature, because, oh, geez, can you imagine if you had negative values here? That's next to near impossible. You can't have a negative pressure or a negative volume. So we need to use Kelvin because it's in the absolute temperature scale. So let's try a little example here. Let's say we have a gas left in an aerosol can, and it's at a pressure of 103 kilopascals at 25 degrees Celsius. So literally it's at roughly about the 1 atmosphere of pressure. If this can is thrown into a fire, bad idea, bad idea, okay? What is the pressure inside the can when the temperature reaches 928 degrees Celsius? Now, from our discussion here, we should be able to kind of get an idea about what it should be. Think about it. We're taking a gas, all right, at 25 degrees Celsius, and now we're making it so the gas is being heated up to 928 degrees Celsius. So our pressure should go up substantially. Would you all agree? Okay, so let's see if we can actually calculate this out. Now, did anyone happen to notice that volume is not discussed here? So that would mean that it is considered to be constant. So one of the things I highly suggest for problems like this is to write down what is given. Okay, so this is continued. All right, so what we have given is the following. We're given an initial pressure of 103 kilopascals. We're trying to find the final pressure. The initial temperature, I converted to Kelvin at 298 Kelvin, and the final temperature, T2, I changed again to Kelvin, which is 1,201 Kelvin. Okay, now again, volume is considered to be constant, and because it's constant, we can actually ignore it in the equation. So we're looking at a relationship between pressure and temperature. So P1 over T1 equals P2 over T2. So what we want to do is do this thing called algebra and solve for P2 and plug in our values. When we solve for it and plug in our values, you can see that my kelvins my temperatures cancel out, and I'm left with my value of 415 kilopascals, which that's what we predicted. The pressure should go up. And if you look and compare our temperatures here, you will see that this is roughly about 4 times the value. Okay, 4 times the value. So we know that we got the correct answer. The pressure should have gone up. Okay, hopefully that makes sense. Let's try another example. Let's look at it from a little more of a complex view. So a volume of a gas-filled balloon is at 30 liters, 40 degrees Celsius, and 153 kilopascals. What volume will the balloon have at 101 kilopascals and 273 Kelvin? So we've got everything but volume given here. And so again, the important thing here is to write down your givens, okay? We were given 30 liters initially, okay? We're trying to find the volume. Our initial pressure was 153 kilopascals. Our final pressure is 101 kilopascals. Our initial temperature was 313 Kelvin, and our final temperature is 273 Kelvin. So the question is, what do you think ultimately should happen here? All right, is it that the volume will go up or will the volume go down? So let's figure it out by, again, using the combined gas law. Okay, so in this particular one, we are using all of the variables, but what we're solving for is V2. Okay, so what I did is I did this thing called algebra. For those of you who don't know what that is, what I literally did, all right, in order to get it as V2 by itself, is I took T2 and P2 and multiplied it on both sides in order to get good old V2 by itself. Okay, that's what I did. So if you look, see, cancels, 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 V2 by itself. Yeah, that's what we get. Okay, now, if we take it, now we can plug in our values. When we plug in our values, I end up with it decreasing slightly to be 39.6 liters. And to double check your work, make sure that your units cancel out. Kilopascals cancel out, your kelvins cancel out as well, so you're left with your volume. Sorry, it increased to 39.6 liters, okay, in comparison to our 30 liters. All right, so let's bring back the mole, ladies and gentlemen, with what we call the ideal gas law. And you're like, what's the ideal gas? What does it mean to be an ideal gas? Well, let's talk about the difference between an ideal gas and a real gas. Now, we don't live in an ideal world, okay? We live in the real world, all right, where bad things happen to good people, let's just say. But let's just say that we lived in an ideal world. Well, in an ideal world, an ideal gas would be one that has absolutely no attractive forces and will always remain a gas. It will never, ever, ever, ever liquefy. It will always remain a gas. However, there are actually small attractive forces between molecules, and at low temperatures, gases will liquefy. Okay? Now, in an ideal gas, gas molecules have a very insignificant volume compared to their container. However, in real gases, if they're compressed, they will liquefy at very high pressures, and gas molecules do have a significant volume. So we're making some very large assumptions. Okay? Now, in order for it to be an ideal gas, really the ideal situation would be at high temperatures and low pressures. Okay, that would be the ideal situation to keep a gas and behave ideally, meaning staying always as a gas, never going through a phase change. So what scientists have been wanting to do is to be able to figure out how much gas they actually have in the unit of mole. So to compare gases, one must know the temperature and pressure at which the volumes are measured, okay? And so we have this thing called standard temperature and pressure, all right? And therefore, scientists agreed to a set of values. Now, this was just an agreement. This was not anything else other than an agreement to compare all gases. And they know this as standard temperature and pressure, which is 0 degrees Celsius or 273 Kelvin, and 1 atmosphere of pressure. This is what we consider to be standard temperature and pressure, okay? And so we try to compare all gases to this ideal situation, this standard temperature and pressure, okay? Now with STP, we can also, this is the best part, we can count the number of particles in a gas, and we call that the molar volume. So when a gas is at STP, it will occupy a volume of 22.4 liters. No matter what the gas is, all right, at STP, it will occupy a volume of 22.4 liters. And you're like, how is that possible? How could it be that any gas will occupy a volume of 22.4 liters at standard temperature and pressure? Well, what's unique about gases is that they can be compressed. And so that's what we need to keep in mind as we go through this, is that gases are unique, is that they can be compressed. Okay, but this is only possible if the gas is at STP. And therefore, if you have the mass of the gas, you can actually determine how many liters of the gas are present, or even moles. Yes, yes, moles. Do you remember this? Do you remember this from a while ago, where we talked about the idea of converting mass into mole and mole into representative particles, but we ignored this section right here? Well, this is, ladies and gentlemen, standard temperature and pressure. And 1 mole of any gas has a volume of 22.4 liters. That is only if it is at STP. Everyone got that? Only if it's at standard temperature and pressure. So how would we use this? Well, let's say we have nitrogen gas at STP and it has a volume of 67.2 liters. How many moles of the gas are present? Well, because it's at STP, 1 mole of any gas, right? Ooh, me needs to learn how to write. 1 mole of any gas is going to have a molar volume of 22.4 liters. Okay, and so if we do this thing called math, we can say that in 22.4 liters of nitrogen, there's 1 mole of nitrogen, so this would provide us with 3 moles of nitrogen. And from this, I can even convert this into grams if I wanted to. So this is a way of us being able to count the amount of gas, the amount of moles in a gas without actually having to count, because we know that it will occupy a volume of 22.4 liters only at STP. But what if it's not at a standard temperature and pressure? What can we do? Is there a way we can actually solve for the amount of moles of gas in the sample? And there is, okay? And here it is. You're like, oh man, seriously? Does anyone recognize this? This is the combined gas law. The only difference is the N here represents, guess what? Oh yeah, you thought it, mole, ladies and gentlemen. It represents mole. Now, this is great, but again, this is for an ideal gas. So what scientists did is they decided, let's make this more simple. Let's make it so that this right here becomes a constant at an ideal situation. Ideal. So let's make it at standard temperature and pressure. Okay, that's for a gas. And what they did is they literally made it so that they would set one side equal to standard temperature and pressure. So if a gas is at standard temperature and pressure, we're talking a temperature of 273 Kelvin. We're talking a pressure of 101 kilopascals, or 1 atmosphere, or 760 millimeters of mercury. And now, if it's at standard temperature and pressure, that means we have 1 mole of a gas that will occupy a volume of 22.4 liters. So if we make one side of the equation in an ideal situation, like, dare I say, this, it always comes out to this value right here, which is oh, yeah, it's a constant, folks. This is the ideal gas constant. That's what we call this, the ideal gas constant. All right, so now instead, we now have R, which represents the ideal gas constant. That's what R is, the ideal gas constant. Okay, and we end up with P times V over N times T, which P is pressure, V is volume, N is mole, and T is temperature. Temperature is always going to be in Kelvin. Okay, all right. So we manipulate this to call it PV equals nRT, or what I commonly refer to it as PivNert. Not pervert, that's different. This is PivNert, ladies and gentlemen. Okay, and therefore the R, the ideal gas constant, is 8.3 kilopascals times liter over mole times Kelvin. You're like, what? What is this? This literally, ladies and gentlemen, is the unit for this number. Yeah, I just said that. That is the unit for the number. All right, so let's try a problemo. You fill a rigid steel container that has a volume of 20 liters with nitrogen gas to a final pressure of 20,000 kilopascals at 28 degrees Celsius. I want to know how many moles of nitrogen does the cylinder contain. So again, the most important thing to do is to write down your givens. You're given the pressure at 20,000 kilopascals. You're given a volume at 20 liters. You're given a temperature at 28 degrees Celsius, but it's got to be converted into Kelvin. And then we're trying to solve for N. So we're going to be using the ideal gas law. We're going to be using PV equals nRT, and there's our R. Our R is a, oh yes, I can't say it enough, this is a constant. And of course you're going to sit there and go, but Mr. Smith, are you going to give this constant to us? Of course I am. Why would I have you memorize that? Not unless you're going on Jeopardy. But yes, I will provide you with a constant, and I will also provide you with all of the equations. It's a matter of knowing when to use them, ladies and gentlemen. So again, we solve for the variable. I like solving for the variable first before plugging in our numbers. So we're trying to solve for n because we manipulated PV equals nRT. Divide both sides by RT. And we end up with n is equal to PV over RT. So here is my pressure at 20,000 kilopascals times my 20 liters times my R, which look, my R has all of the units there, along with my 301 Kelvin. Now notice, the Kelvins cancel out, the liters cancel out, the kilopascals cancel out, and I am left with only mole. And so I end up with 160 moles of nitrogen. Now, can I make this problem one step harder? Yes, I could say solve for the mass of the gas. And if I wanted you to solve for the mass of the gas, then what you would do is then look up the molar mass of the gas. So for every 1 mole of N2, that would be a molar mass of 28 grams of N2. So you could actually get the mass of the N2. So it's a matter of practice, ladies and gentlemen, and that's what I want you to do next.